Hey everyone, you know that feeling when you're staring at a tough stats exam and it just feels impossible? Well, you're in the right place. Today, we're not just looking at an exam, we are going to crack it wide open. We're taking some really challenging advanced statistics problems and breaking them down, step by step, until they make perfect sense. All right, let's get into it.
So here's our game plan. We're going to tackle this in 3 parts. First, we'll lock down the fundamentals with core concepts. Then, we'll roll up our sleeves and solve some applied problems. And to wrap it all up, we'll dive into a real-world case study. Okay, let's kick things off with Section 1, Core Concepts. Think of these questions as the foundation. They're designed to make sure we've got a solid grasp of the big ideas. If you nail this part, everything that comes next gets a whole lot easier.
And our first problem is a classic. We've got 2 different models, a simple one and a more complex one, and we're being asked about their R-squared values. But here's the catch. The question isn't asking what's right, it's asking what isn't necessarily correct. This is all about spotting that one subtle but crucial trap.
Before we look at the options, let's just do a quick refresher on R-squared. All it really measures is how much of the story our model can tell. If our outcome variable has a lot of variation, a lot of wobble, R-squared tells us what percentage of that wobble our predictors can explain. A high R-squared is good, but as we're about to see, it doesn't tell the whole story. So let's look at our 2 models. The simple one, with just one predictor, explains only 12% of what's going on with sales. Kind of weak, right? But look what happens when we add 2 more predictors. Boom! We jump all the way to 53%. Clearly, the bigger model is doing a much better job overall. But is every single part of that model actually helping?
And that right there is the trap. A high R-squared feels great. It feels like a big win. But you have to think of it like a team's final score. It tells you the team won the game, but it doesn't tell you if every single player on the field had a great performance.
Which brings us to the answer, E. The statement that all 3 regressors impact the sales significantly is not necessarily true. It's totally possible that 1 or 2 of those variables are absolute superstars doing all the heavy lifting, while the third one is just along for the ride, adding nothing but noise. To find out who the real MVPs are, you have to look at their individual stats. And, in regression, that means checking the p-value for each and every coefficient.
All right, with that theory locked in, let's move on. Section 2 is where we stop just talking and start doing. It's time to put that foundational knowledge into practice and actually crunch some numbers to solve some real hands-on problems.
Okay, picture this. A small dairy startup claims their fancy cheese lasts for 3 weeks. That's 21 days. We've got data from 8 batches, and our job is to calculate the Wilcoxon signed rank test statistic. Now that name sounds intimidating, I know, but trust me, it's really just a recipe we need to follow.
And here is that recipe, our plan of attack. It's just 5 simple steps. We'll state our hypothesis, find the differences from that number, rank those differences, add up the positive ones, and then standardize the whole thing. Let's walk through it.
So first things first, we take each of our data points and subtract that target of 21 days. The cheese that lasted 15 days, that's a difference of -6. The one that went 24 days, that's +3. Next, we ignore the plus or minus signs for a second and just rank how big the differences are. A difference of 1 is rank 1, and so on. Then we just stick the original positive or negative sign back on.
Now for the final calculation. We take all those positive ranks, in this case just a 1 and a 3, and add them up. That gives us our W value, which is 4. But what does 4 even mean? Is that a big number? A small one? We have no context. So we have to standardize it. We use these formulas to figure out what the mean and standard deviation would be just by random chance, and then we plug it all into the Z formula.
And when we run all those numbers, we get our answer. The standardized test statistic we were looking for is -1.96.
So, the correct choice is D. And the big takeaway here isn't just remembering how to do the math. It's knowing that for this kind of test, we can use what's called a normal approximation to get a standardized Z-score. That's the key that unlocks the whole problem.
All right, time for the final boss, the case study. This is where the training wheels really come off. We get a messy, real-world business problem, a data set, and we have to figure it out. This is statistics out in the wild.
So let's set the scene. We're stepping into the shoes of Miss Shreya. She's an analyst for a superstore, she's got data on 5,000 orders, and she needs our help. This is what makes case studies so great. It's not just about numbers, it's about solving real problems. And her first question is a really important one. She wants to know if the profit data follows a normal distribution, that classic bell curve shape. This is a super important first step because a lot of other statistical tests assume your data is normal, so we've got to check. The right tool for this job? A chi-square goodness of fit test.
So, the whole idea behind this test is pretty simple. We're just comparing what we actually observed in our data to what we would expect to see if the data fit that perfect bell curve. That last column there is basically measuring the gap between reality and theory for each group. We're on the lookout for really big gaps.
When we add up all those individual gaps from that last column, we get our grand total, our final chi-square test statistic, 133.75. This one number summarizes just how different our data is from a perfect normal distribution. The bigger the number, the worse the fit.
So, is 133.75 a big number? To decide, we need a benchmark. We look up something called a critical value, which for this problem is 5.99. Think of this as the line in the sand. If our calculated number is bigger than this, it means our data is significantly different from normal.
And yeah, the decision here is crystal clear. Our number, 133.75, isn't just bigger than 599, it's in a completely different ballpark. So we confidently reject the null hypothesis. In plain English, that means Mrs. Shreya's profit data is absolutely, positively not normally distributed.
So let's just quickly recap the big lessons from today. Number 1, a high R-squared is nice, but it doesn't mean all your predictors are useful. You have to check those p-values. 2, tests that sound scary, like the Wilcoxon, are usually just a clear step-by-step process. And 3, always check your assumptions. Use tests like goodness of fit to make sure your data is what you think it is. And we'll leave you with this final thought. We didn't just find a few answers today. We learned how to deconstruct the problems themselves. So the real question is, now that you've seen this way of thinking, this framework for breaking things down, how is it going to change the way you attack the next statistical challenge that lands on your desk?